Hi everybody. I want to go with you. I want to go with you through this Mathematica notebook here. And what we will do here, we will explore a little bit the solutions which we found in class of the particle in a box, and also a bit look at it, what it means in the context of the properties of quantum mechanics, which we found so far. So here at the beginning of the notebook, what we do is we define some constants, so the usual constants. So here's the h bar, the Planck's constant over 2 pi, elementary charge, speed of light, and then also the mass of the electron. So we do that here, we define that quickly. And then we define the width of the box, so we say it's just a nanometer, and then we get the falling value for the energy. And then here we make, for the start, we make some plot of the possible energy values. We do this in units of electron volts. We do this for the first 5 quantum numbers. And then we just plot it here for some distance 0 to 5. It doesn't really matter. We just want to make here a nice picture. So we see we get this typical energy eigenvalues of the particle in the box. Next, we would like to determine the normalization of our wave functions. Remember, our wave functions are given here by some normalization constant, and then here the sinus of pi n x over L. That's how we determined them in class. Now you want to ask Mathematica to do this integral for us. So we ask it Mathematica, we tell Mathematica to assume that n is an integer number and is positive. And now we take here a, the square of this wave function. So here's a sinus pi nx over L squared. And then we integrate this from 0 to L, so the size of the box, because outside of the box the wave function is 0. And then we tell Mathematica that this condition here should be, this result here should be equal to 1. And to fix a accordingly, and then of course it is not difficult, it's just two solutions, so it's a over root 2 over root L. And then this we can define our wave function, so we put down here in front the normalization factor. Now with our L is defined now, which is now 1 nanometer, then our wave function, the solution here. And then make a table of this wave function, and we just make it in the tables in different colors. So now blue will correspond to n equals 1, purple to n equals 2, and so on the fourth. And then that's how the picture looks like. So that's now our first wave function, n equals 1, n equals 2, that is now purple. And you see like each wave function has more has more nodes if you go to higher values of n. So that's a different picture one can do here. So now you can separate them, so you just separate them by a factor of n squared, not to have them separately. And to see actually better the functions, no, but there's nothing really special about it here. So finally, we verify here the property of stationary states. So we put here now our energy dependent, our time dependent factor in front, so the exponential minus I energy n t over h bar. And then we plot that, and then we plot here the square of this absolute value of squared of these wave functions. And of course, as we know from theory already, this time dependence factor will drop out for the stationary states, and then we plotted the time dependence, and you see there's no time dependence, they're the same all the time. And we made here this for a fixed value in x. So here x was 0.3 L. Now here we take another value, 0.55 L, and you see, of course, there's again nothing changing. Also, the absolute value, the value of the wave function, it might change when you go to different positions. So you see the plot is different, but it's all independent on the time. So next, we would like to take a look how this all affects now the position and expectation values for position, momentum, and also the corresponding uncertainty. So let's take first here a look at psi squared. So essentially, that's the probability squared, the probability density, which we get from this wave function. So we see, for instance, for the zero solution, we would expect here that the most likely position here would be in the middle. For the other ones, also by symmetry, we would expect it's in the middle. And we see actually that's really the case. So we calculate here the expectation value for x. So we put us here the same integral as up here, but now I put here also the x inside here to get the expectation value of this operator. And we just normalize here by a factor 1 over L, because we expect here something of the order of L over 2. So we would like to take out this factor of L to get here a nicer number here. And then we see we really get for all states, the expectation value is exactly in the middle. So maybe if you look at the states here, it's actually not so surprising because they're pretty symmetric. And now we can calculate the fluctuation, and here the results. So to calculate that, you do exactly the same as before. It's just you change the x to the x squared. So here was an x, and here's now the expectation value of x squared. And you see now here the expectation value depends. It is changing with the position, and now calculate the uncertainty by subtracting the expectation value of x squared minus the expectation value of x squared. We obtain our following values, and we can plot this now, so we can make a picture. And then you see now that here, actually, the first state, the n equals 1 state is actually a rather low uncertainty, but then the uncertainty is rising, and it's sort of now approaching as a more or less constant value of 2.8 or so. No? So it's kind of also interesting observation that the uncertainty actually in the position is actually lowest for the lowest energy state, and the higher states have a higher uncertainty. And now we can also calculate the expectation value for momentum. So that we have to include the derivative of a one-wave function with respect of x. So that's the d operator here in Mathematica, and then here the factor minus I, which you have to include here. So we can do that, and then we get here always 0, so there's nothing. So actually the expectation value of momentum is 0. But now we can calculate the fluctuation. So we do here the same as before, but now here minus I squared, and then the second derivative here. So x, 2, that's how you get the second derivative in Mathematica. And then we do that, and then we get finally non-zero values. Then we still have forgot here now to multiply this here now with h bar squared, because we actually, so we should do with x bar squared. And then we can also calculate now the uncertainty in the position. So for this we have to divide now by, no, sorry, that was wrong here. There should be only an 8 because we didn't take here the square root, so it was a factor of h bar. So we get that factor here. Then for the position, we still have to remove here this factor of L, one of L, which we put there here. And then finally we can combine here. We can multiply the uncertainty in momentum with uncertainty in the position and divide it by a factor of h bar. And then we see here that again here the lowest state gets pretty close to the lowest bound of 0.5. While for the higher states, the product of the two uncertainties is actually way above the Heisenberg bound. So finally, we'd like to take a look at more close look at time evolution, how real states would change with time. So we just make here up now here some states which we'd like to involve with time. So it's just like just a combination of two theta functions. So it looks something like this. So we have here first here a 0, and then it jumps to some value of 1, which is we have to normalize, and then again 0. So that's not, of course, a realistic wave function. A realistic wave function, it should be continuous. So we'd expect something of that type here. But for the moment for us, that's enough. We just would like to have something that will tell us if it is more as a particle here in the middle. And then we'd like to see how this particle here, which we put here somewhere in the center, how it will evolve with time. So maybe even to make it even more nicer, we could move it a bit to the left, so we can put here. So we tell it to start a bit over here, and then maybe here 8, then 3 8. So this would look like that. Yeah? So now we have the particle here a bit more to the left. So maybe actually that is even nicer. Now we can normalize this state, even though it's not a real state, but we can still try to normalize it. Now we have our normalized state, so we multiply now this norm factor here in front. So that is now fine. So we can also still plot this if you wish like. So plotting a normalized state, that's how it looks like. Yeah, so I can just have different values, and it gets pretty huge here because it's a very short, very small very small box what we have here. So now what we'd like to do now is we would like to make an expansion in the eigenfunction of this initial state here. So essentially we would like to calculate the coefficients of the Fourier series. So that means we have to calculate here the integral over the energy eigenstate of psi n. So we could also write here the psi n, but now I wrote here the thing separately in sinus and the normalization factor. And then we combine it here with this state which we want to analyze. And then we tell Mathematica to assume that n is again an integer number and is bigger than 0, because that's how it is. And then Mathematica can calculate these coefficients for general n, so it becomes the following result here. And now we can just take a look at them. So actually, that's how they look like. So we have here the first value and the second value. So we can now maybe turn off the joint one. We can say this false. We don't connect the points. So you see here that's the first point here. Then the second one is higher, then there's the third one, it goes down, then it's 0, then something is negative, and then it's slowly converging to the value. No? So you see at some point it will be It will be very small, and actually the series would be converging. The imaginary parts there, they are 0. We can look at them, but there's nothing exciting here because it is that's real now, so there's nothing to be expected. And now we can see how well this function here is converging. So we see we only take here now 10 terms, so we make it a sum from 1 to max. And max is now 10 terms, so we take it 10 terms for our complete sum here, which in theory runs to infinity. So we see it's an approximation, but it's not the best approximation. Now we take 20 terms, so it gets better. And we take 30 terms, better, but still not perfect. Even with 40 terms, we kind of still not really there. Now we can take 80. So for 80, we'd say, okay, maybe we call it a day, maybe that's enough now. And I think we will use now in the following study now to study time dependence. We use now the approximation with 80. Then we just take this as here as our corresponding state. So now we define again here, okay, omega n is now energy n over h bar. And then we have here now our wave function with time dependence. So again, we sum here over all of up to 80 here. And then we have here our time dependence here. We can still take this factor here actually now and fix. So maybe we can do this now here. We can take this function here and we call this now function h here. And now we would like to calculate the normalization of this function because it's a bit different to the original function. So we take the function h on x and we take the time equals 0. And now we want to integrate now from 0 to L. And here we take the square, of course. And then we see it's not directly 1, so we can call this now again. So norm 2, if you want. And okay, and then the square root of that one here. And then 1 over the square root, so we can get this normalization factor here. And then just to make it call it a day, we take it the real part. So we get that's our normalization factor. Now we put here this norm in front. And now we make here again this integral, but now with g, that should be all well normalized as we would like to have it. That's now g and integrated, and that didn't work out at all. So what's wrong now here? What we were wrong? Oh, this is not norm, but it's norm 2 here, right? That was a mistake. Norm 2. Yeah, now it's 1. Yeah, so now we have here a function which is very nicely, which has yeah, so also to get rid of the real part, we could take the absolute value, so we really kill all imaginary parts. So yeah, so then you have really the wave function normalized to 1. Now we can just see how this stuff is changing with time. So maybe call this now 10, so more things. So that's how the function will look like. So we see that's how the state evolves. Yeah? So it starts here, it starts at some point, and then you can stop here now a bit. So here at some point you might be a huge probability to be here at that point. Then it goes on. Tell it to slow it down a bit. So this is how essentially the particle is basically essentially going forward and back. No? So there's always different region where it's more likely to be and less likely to be, but you see that the probability whether you can find a particle, because you plot here the probability essentially, it's changing with time, yeah? And this is like what a real particle would do as well. No? So we see kind of there's some motion going on, and we can describe this now in terms of our quantum mechanical picture. So we can also now check now whether our probability is conserved over time, so we can evaluate this integral here over different time steps, and I hope it works now always out correctly. So probability is conserved, so there's time. So our evolution is really conserving probability. The particle is not disappearing, or there's no new particles coming in, which of course is very nice. And then here in the end there's another game here, but here's some mistake factor of 2 here somewhere. So I think I stopped it here. And thank you very much for paying attention to this video. And I will post you the Mathematica notebook as well, in case somebody wants to play with it by himself. And but you can take a look at this, and I hope it's useful for you. So let me just see how I can stop here. So I think here stop.